Welcome to the course on an introduction to information theory. So we will continue our discussion on block to variable length code. In this lecture we will talk about optimal block to variable length codes, which are also known as Huffman coding. And then we will talk about how can we encode a source. We have so far talked about coding a single random variable, how the same concept can be extended to coding a source of length L. So the first property which I am going to show for optimal prefix free code is as follows. So let us first consider a binary prefix free code. So we are considering our code word consists of zeros and ones. So a binary tree corresponding to an optimal binary prefix free code does not have any unused leaves. So the first claim that we are making is, if we have a binary prefix free code which is optimal, and if we map it to a binary tree, then there should not be any unused leaves in this binary tree. Now if there are, so let's prove this. So let's do by method of contradiction. So let's say if there are unused leaves, then these unused leaves must be at the maximum depth. Otherwise we can always bring in a code word from higher depth to smaller depth, in the process reduce the expected code word length. So if at all there are unused leaves, they must be at the maximum depth, otherwise the code would not be optimal. Now so if they are at the maximum depth, then one of these two things can happen. Since it's a binary tree, so there are two leaves. So either one of this is assigned a code word and other one is just an unused leaf, or we could have this as unused leaf and a code word assigned to this. Now in this situation, you can see in either case I can move this code word here, I can move this code word here, and in the process I am decreasing the expected code word length by 1. So by deleting the last digit of this code word, we still have a prefix free code, and this new code has smaller expected value of W. Hence my earlier claim that there are unused leaves at the maximum depth for optimal code is false. So by method of contradiction we have shown that this cannot happen. So if you have an optimal binary prefix free code, then the binary tree corresponding to this prefix free code cannot have any unused leaves. The next result which I am going to make is, if there is an optimal binary prefix free code such that two least likely code words, let's call them UK-1 and UK. So UK-1 and UK are the two least likely code words. So they should differ only in their last digit. So if you have two least likely code words, they should differ only in their last digit. So the proof is like this. So this is our least likely code word, okay, and the next least likely code word is this. So we have situation like this. So we have a node at highest depth where you have two code words UI UJ, UI UJ. We can have something like this. Now what we can do is, if let's say our J is not equal to the least likely code word, then we can always replace UJ by code word corresponding to UK. So if J is not equal to K, we can always switch the leaves of Uj and Uk, because Uj, probability of Uj is more than probability of Uk, and we are moving Uj to a smaller depth. In the process, this swapping would not increase expected value of W. In fact, it can decrease. It is possible that the expected value of W can decrease. So if this J is not, Uj is not same as the least likely code word Uk, I can always swap wherever my Uk was and I bring it here, and I can move Uj back to where Uk was, right? And this process would not increase my expected code word length. Similarly, if my Ui is not same as Uk minus 1, which is the second least likely code word, then I can always swap where my Uk I minus 1 was and bring it here and move Ui back to where Uk minus 1 was. Now since probability of Ui is more than Uk minus 1, and since my Ui was earlier at the maximum depth, when I swap them, my expected code word length is not going to increase. In fact, it can decrease. So hence, what I have shown you is, if at maximum depth you have code words like this Ui and Uj, then I can make this Ui Uj as Uk and Uk minus 1 without actually increasing my expected code word length. And hence, if I have, and what is my optimal code? The one which will minimize my expected code word length, expected value of W. So what I have shown you is, I can have a situation where these two least likely code words are part of the leaves at the highest depth, and this will result in average code word length which is minimum. Hence, we can say that if they are part of the same coming out from the same node, then these two code words will differ only in their last digit, because before this the path from root to this node is same for both these code words. So two least likely code words will then differ only in their last digit. So what we have shown is the new optimum code, which has the minimum expected value of W, will have two least likely code words, and they will only differ in the last digit. That is because from root to this node the bits are all same, they are only differing in the last digit. So now let us give us the algorithm. Using these two results, we will give an algorithm for constructing optimal binary prefix free code. So we are interested in optimal prefix free code for a random variable u which takes k different values. So let us designate these k different values as u1, u2, u3, uk, and we assign probabilities to each of these vertices, which is equal to the probability of ui's, and we will designate these vertices as active vertices. Step 1, we create a node that ties two least likely active vertices. Please note, we have said in the previous lemma that for optimal binary prefix free code, two least likely code words will differ in only one location, one last bit location. So we consider two least likely active vertices and we combine them and join them and create a new node, and the probability of that node is equal to sum of the probabilities of the two vertices. So this new node that we are creating, its probability is equal to the sum of probabilities of the two nodes that just got joined. We are going to activate this new node and deactivate the two vertices that were joined. Okay, so now those two vertices got deactivated, but we have created a new active node which has probability equal to sum of the probabilities of those two earlier vertices. Now we continue this process until we are left with only one active vertices, and if that is the case, we will make it root vertex and we stop, and that is how we are going to construct optimal binary prefix free code, which is our Huffman code. So let us take an example. We have a binary Huffman code which takes 6 different values. So U1 has probability 0.05, U2 has probability 0.1, U3 has probability 0.15, U4 has probability 0.2, U5 has probability 0.23, and U6 has probability 0.27. So first thing we do is we just write down a vertex corresponding to each of these 6 possible values of U, and we write the corresponding probability of these UIs, which is given by here. Now note, we are interested in binary Huffman code, so there are 2 branches from each node. So we look at 2 vertices which has the least probability, and which are those 2 vertices? This one corresponding to U1, another corresponding to U2. So what we do is we combine these 2 vertices and we create a new vertex which is a sum of probabilities of this and this. So this new vertex which is formed is its probability is new node that we are forming has probability 0.15. Now we deactivate these nodes. So now the active nodes are this one, this, and this. Okay. Next step. What are the 2 least likely active nodes? So clearly the 2 least likely active node at this point is this one and this one. So we combine these 2 and create a new node. Now what is the probability of this node? The probability of this node is probability of this node, which is 0.15, plus probability of this node, which is also 0.15. So this probability is 0.3. Now we deactivate these nodes. So now our active nodes are this one, this one, this one, and this one. Okay. Now among these 4 active nodes, which 2 have the least probability? The one corresponding to U4 and U5. So we combine these 2 and create a new node. And what is the probability of this node? 0.2 plus 0.23. So that is 0.43. Now we deactivate these nodes and we activate this node. So now our active nodes are this one, and this one. So we have 3 active nodes now. Now out of these 3 active nodes, which one have the least probability? 0.27 and 0.3. So we combine these 2 nodes, we create a new node whose probability is sum of probabilities of these 2. So 0.3 plus 0.27, that is 0.57. Now we deactivate these 2 nodes. Now what are the active nodes left now? One is this node, another is this node. So we combine these together and we get a new node. This probability of this node is 1, and now we have only one active node remaining, so we make it a root node. Okay. And now each of these 2 branches which are starting from each of these nodes, we assign one of them as code bit 0, other as bit 1, right? And now you can trace back the path from root to each of these code words to get the corresponding code word. So, for example, U1 is nothing but 0, 0, 0, 0. So, that is my code word corresponding to U1. What is U2? 0, 0, 0, 1, 0, 0, 0, 1. What is U3? That's 0, 0 and 1. That's U3. What is U4? U4 is this one. So that is 1 and then 0. What is U5? U5 is 1, 1. And similarly, what is U6? U6 is this one. So that's 0 and 1. So this is the optimal binary prefix free coding for a source which has 6 possible values and whose probabilities are given by this. So this is the optimal Huffman coding for this particular source. Now, we will try to extend this result for a DARE prefix free code. So first we are going to prove a result which says that number of leaves in a finite DARE tree is given by D plus Q D minus 1, where Q is number of nodes not counting the root node. So what we are saying here is the number of leaves in a DARE tree is given by D plus Q times D minus 1. So how do we prove this result? So let's look at, so let's construct a tree from a root. So if you are constructing a tree from a root, so initially what's going to happen? Initially you are going to have D leaves starting from this root. Now initially you will from a root you will have D leaves. Next, if you try to extend any of the leaves, what's going to happen is you are going to create D new leaves, but in the process this leaf which was earlier a leaf has now become a node. So effectively you are adding D minus 1 leaves. So then at each subsequent step, if we are trying to extend a leaf, we are getting T new leaves, however we are losing one old leaf because that particular leaf has now become a node. So if we do Q such extensions of this tree, what we are going to get is we are going to get D plus Q times D minus 1 number of leaves, where Q is the number of leaves not counting the root leaf, because if we start from root leaf we get D new leaves, but subsequently when we are trying to extend a leaf we create D new leaves, however that particular leaf now becomes a node. So effectively we are adding D minus 1 new leaves. So this is the total number of leaves that we can have in a DARE tree. So first result we are going to show for a DARE prefix free code is optimal DARE prefix free code is there are at most D minus 2 unused leaves for an optimal DARE code, and all of them are at the maximum length. Now proof is very similar to the case for binary. So if there are unused leaves and if they are not at maximum depth, then we can always decrease our average code word length by moving leaves from maximum depth to those locations. So if at all there are unused leaves, it has to be at the maximum depth. So this is clear that if there are unused leaves, they have to be at the maximum depth. Now, how many such unused leaves can be there? So note that there are maximum D leaves possible, right? This number of leaves is basically we can have D leaves possible. Now if there are D minus 1 unused leaves, that means only one of the leaves has been used, all others are not used. If such a situation happens, we can always move this leaf to this node without increasing our average code word length. Hence, we cannot have D minus 1 unused leaves. So at most we can have D minus 2 unused leaves, and those D minus 2 unused leaves have to be at the maximum depth. Otherwise, we can always reduce expected code word length by moving some of the code words to lower depth. Now, in the previous result, we have shown that at most there can be D minus 2 unused leaves, and those unused leaves have to be at the maximum depth. In this result, we are going to calculate how many unused leaves are there in an optimal DRE prefix free code. So if you have a random variable u that takes k different values, where k is greater than d, then the remainder obtained by dividing k minus d into d minus 2 by d minus 1, that number will give us number of unused leaves in a DRE prefix free code. And remember, all of these unused leaves have to be at the maximum depth. So number of unused leaves is given by number of leaves in a DRE tree minus number of possibilities of this random variable u, which is k, because u takes k different values. And what is the number of leaves in a DRE tree? That number is given by d plus q times d minus 1, where q is number of nodes minus the root nodes. So number of unused leaves is then given by this expression. Now I do some algebraic manipulation, I can write this as this particular way. So you can think of as number of unused leaves as, if I divide d minus k by d minus 1, whatever remainder I get, that is the number of unused leaves. Or I can do some more manipulation. If I add k minus d into d minus 1 to both sides, I can write this expression in this particular fashion. So I can then say that if I divide k minus d into d minus 2, if I divide this by d minus 1, whatever remainder I get is my number of unused leaves. So for an optimal DRE prefix free code, the number of unused leaves are given by, if I divide k minus d into d minus 2 by d minus 1, whatever remainder I get, that is the number of unused leaves, and those unused leaves must be at the largest depth. So then I can write that there is an optimal DRE prefix free code for a random variable u with k possible values, such that there at most such that the d minus r least likely code words, they differ only in their last digit, and this R is computed as we shown earlier by dividing k minus d into d minus 2 by d minus 1. Now this proves that d minus r least likely code words differ in only one position. This proof is very similar to the proof that we did for binary optimal prefix free code, where we showed that the two least likely code words differ in only one bit location. So I am not going over this proof. This is very similar. You start off with some code word ui, uj, and if they are not the least likely code words, you can always swap it with least likely code words, and you can show that this process of swapping would not increase your expected code word length. So this proof is very similar to the proof that we did for optimal binary prefix free code. So then I can state the algorithm for optimal prefix free code for a DRE prefix free code. So you have u that takes k different values. Let's designate those vertices as u1, u2, u3, uk minus 1, and let us assign probability PUI to each of these UIs. Now we will designate these vertices as active vertices. The first thing that we are going to do is we are going to compute how many unused leaves are there at the maximum depth, that's R. And how do we compute that? That is computed by dividing k minus d into d minus 2 by d minus 1, and whatever remainder we get, that is my number of unused leaves. So in the first step, what we do is we create a node that ties together d minus r least likely vertices with d minus r branches of a DRE branch. So note that since r of the leaves are unused and total there are d branches, so in the first step we are going to combine only d minus r vertices, d minus r least likely vertices, and we will assign probability to this newly created node, which is nothing but sum of probabilities of these d minus r vertices. We will activate these vertices and deactivate the d minus r vertices that were joined. Now in the next step we are going to combine, because remember the unused leaves can only be at the maximum depth. So the next time when we combine, we are going to combine d vertices, d active nodes together and combine them into a new node whose probability will be sum of probabilities of these d nodes, d vertices, and we will continue this process until we are left with only one node, and that would be our root node with probability 1. So let us illustrate this Huffman coding algorithm with an example. So we are considering a ternary Huffman code. So D in our case is 3. We are considering the same example which we use for binary Huffman code. So in this example my k is 6. So u takes 6 different values, u1, u2, u3, u4, u5 and u6, and these are the corresponding probabilities of these ui's. Okay. The first step is I write down all my ui's and the corresponding probability. So this is my u1, u2, u3, u4, u5, u6, and these are my corresponding probabilities of these ui's. Now the first step is I need to compute how many unused leaves are there. So how do I find unused leaves? I divide k minus d d minus 2. I divide this by d minus 1. So what is k minus d? That's 3. D minus 2 is 1. So 3 divided by 2, remainder is 1. That means I have, in this example, I have one unused leaf. And remember that unused leaf has to be at the maximum depth. So what do? Then the first step, I only combine two vertices which have the least probabilities. And what are those two vertices? This is u1 and u2. So I combine these two, okay, and this is my new node which has probability equal to sum of these two nodes. This is 0.15. Clearly I have a unused node here. Next, I deactivate these nodes, and now my active nodes are this one, this one, this one, this one, and this one. So I now have to pick 3 least likely active nodes, and what are those? That is 0.15, 0.15 and 0.2. So least active nodes, least likely nodes are these. I create a new node. Its probability is given by sum of probabilities of these 3 nodes. So it's 0.15 plus 0.15 plus 0.2. So that's 0.5. And now I deactivate these nodes. So at this point my active nodes are this, this and this. So I have 3 active nodes. I combine all of them, and what I get is, so 0.5, 0.23 and 0.27, I get basically this. So I get this, I get this, and I get this. So this one node left, I deactivate these nodes, so there's only one active node left, so I make that as my root node. And next I assign a bit to each of these 3 branches. I am calling it 0, 1, 2, and then you can trace back the path from root to each of these code words, and that's your code word. For example, u1, what is u1? u1 is this 2, 0, 0, that's your u1. u2 is 2, 0, 1. Similarly, you can find out the corresponding code words for each of these UIs. So again I repeat, the difference from the binary case here is, here in the final step, in the maximum depth, you can have some unused leaves. So you have to first find out that. So in the first step, you are only going to combine D minus R active vertices, and subsequently you will be combining D vertices until you are left with only one vertex, which is basically your root. Now what we have done so far is, we have shown you how to encode a single random variable. So we have a single random variable u which takes k different values. How can we optimally encode it using block to variable length coding? Now what about if you have block of data? So I have an information sequence u1, u2, u3, and I want to encode block of, let's say, L blocks of a block of L bits. How do I apply whatever we have studied so far to a block of data? So what I need to do then is, I have an information source which is giving me these UIs. I need to partition this into blocks of data. Let's say I am partitioning this into source parser. What it does, it divides the output sequence into messages which will be encoded by this source encoder, message encoder. So it's creating blocks of, so each block will have L bits of UIs. So we consider an L block source parser. So you can think of as V1 as U1 to UL, V2 as L plus 1 to 2L, V3 as U2L plus 1 to U3L. Like that, basically the source parser what it's doing is you are getting bits of data, it's partitioning into a block of L bits. Now you are sending this block of L bits to the message encoder, which is going to do block to variable length coding. So we can show that there exists a prefix free code, a DRE prefix free code for this block of L bits which are coming from a discrete memoryless source, which satisfies this condition that average code word length per block size is upper bounded by this and lower bounded by this term. Now we already have computed bounds on optimal code word length for a coding of single random variable. We are going to extend that result for the case when we want to encode a source of length L. So we have a source U which consists of L components of these UIs. So this is LIID component. So in that case, uncertainty in V can be written as uncertainty in U1 plus uncertainty in U2 plus uncertainty U3 up to UL. Since they are identically distributed and they are independent, H of U1 is same as H of U2 is same as H of UL is same as H of U, and since they are independent, so we can write uncertainty in V as L times H of U. Now we know if we have a prefix free code for V, we have shown earlier that expected code word length is lower bounded by entropy by log 2 and it's upper bounded by entropy by log 2 plus 1. This we have proved in the earlier lecture. So if we plug in the value of uncertainty in V, what we get here is L times H of U by log of D. This must be less than expected code word length, and expected code word length is L times HU log D plus 1. Now if we divide by 1 by L, what we get here is this relation that average code word length per this length L is basically lower bounded by this quantity entropy and upper bounded by this quantity. Now of course if L is very large, you can see this upper and lower bounds are very close. So with this we will conclude our discussion on block to variable length coding. Thank you.